Cloud. Good morning. We were just talking about what's the point of simulations. Oh, nice. Okay, good. I'll check on that timeline. Just going back to the chat here. I'll check and see if I can find something like that. They've got all kinds of cool stuff. Okay, so what we were talking about was just briefly, what's the point of doing these simulations? And so we don't need to do them, but the idea is that we're going to pretend that we've pulled many samples, so thousands of samples, to be able to determine what distribution did it come from. And so that's kind of a weird idea. And so last day, for some review, right, we looked at the simulation of sample proportions. And so we looked at the simulation, or we simulated. We didn't do 1,000. I think I pulled it down to 100 or something like that, but that's okay. We simulated drawing many samples from a population. Oops. Come on. From a population. We do this, so we look at, when we pull a sample, so in real life, IRL, in real life, we only pull one sample. We only pull, I'll say, I should say collect. I shouldn't say pull. We should usually say we pull a sample, but we only collect one sample, right? But to find probabilities associated with that sample, right? For example, the sample proportion, we need to know what distribution did it come from. Okay, so we only collect one sample, but to do or to find, I'll say, to find probabilities associated with I'll stick to the one that we're looking at, the sample proportion. With the sample proportion, we need to know what distribution it comes from. So what kind of what shape would it come from if we looked at many sample proportions? And so that's what we looked at, and we actually found the sampling distribution. And so, oh, I'm not set up here. How about that? Move my mic closer. So with the sample proportion, we need to know what distribution it comes from. So that's a little bit tricky. And so to do that, we pretend to look at many samples, right? So thousands of samples. And so to do that, we pretend to look at thousands. Maybe I should write the word. Thousands of sample proportions. And then what we found last day, right? And so we did this and found that p hat, so the sample proportion, follows a normal distribution, technically with a center of the population proportion, right? Do we deliberately make samples? No, so those will happen naturally. So what happens is we naturally get this normal distribution. And so that's kind of cool. We're going to get these kind of extreme samples that we collect, but they're not very common, right? And so that's why the curve gets smaller there. And so, but they still happen. So if we have a normal distribution with a center of P, the population proportion, and I'll make it nice and big here, we said we're going to have a spread of the square root of P times 1 minus P over N. Right? And this, we call it our standard error of P hat. Standard error, or SE, of P hat. So what we can write is we can summarize that as SE subscript P hat. Yeah. The problem is that we don't know what P is. We don't know what the population proportion is. And so for us, in our calculations, we're just going to replace it with P hat, right? So since we don't know P, we use P hat instead for an estimate of the standard error. We use P hat to calculate the standard error. Right? And so this gives us an estimate for the standard error, which gives us an estimate for the standard error. So what we're going to say is that for us, the standard error of P hat, when we go to apply it, it's not going to be P and 1 minus P, it's going to be P hat times 1 minus P hat, or Q hat if you prefer, which I do, but for now, I'll use 1 minus P hat over N, right? Or P hat Q hat over N. If you're like me and you like to use Q's instead of 1 minus P. Look at this, I cut down 4 characters, 2 brackets, 1 minus, instead of just wrote Q hat. Anyways, so we have this estimate for the spread. The standard error is just the spread of P hat. Okay. And so this here, and maybe this is the spread or the variability, but people don't really like it when I use the term variability, but it's just the spread, right? And so so the spread or the variability of P hat, because we understand that P hat is not going to be exactly the same as the population proportion, right? Or yeah, but we know, or we hope that it's going to be close, right? And so we know P hat, right, will have some error, right? And so it's going to be a little bit different so that the error amount different from the population proportion. We know p hat will not be exactly the same as p, the population proportion, but we expect it to be a good estimate. But we expect it to be a good, I'm going to start calling it a point estimate for P. Yeah. Good. So that's kind of where we left off, and that's going to be an important concept, but really all we need to remember is that, okay, as long as we've satisfied some conditions, then we can assume that p hat came from a normal distribution, right? And so we need to check those conditions before we go ahead, right? But once those conditions have been checked, and they're always going to check out, but we still have to go through the motion and maybe have like a little mind stopper that says, okay, I have a small sample size, so it might not work out. So then really pay attention to checking those conditions. But in general, they're always going to check out. Okay, so what were those conditions? And so to be able to assume that we have a normal distribution, we need to check conditions. To be able to assume p hat comes from a normal distribution, we need to check conditions. The first one is, do we have a random sample? And so a random sample is the easiest way to make sure that we have independent observations, right? And so we need to check that we have independence which we checked by saying, okay, a random sample will be the easiest way to be able to assume independence. Will be the easiest way to be able to assume independence. Independence. Got squished there. Okay. I'm going to throw in the optional thing that we can check. So another thing that contributes to independence is if we make sure that our sample size is less than 10% of the population. And less than 10%, right, ensures that we have independent observations. So the reason here is a little bit weird because n less than 10% of population, because we always, we know, probably even heading into this course, that large sample sizes are a good thing, and they are, right? Because it makes our calculations more robust, right? And so, and our conclusions more robust. So large sample sizes are a good thing. But when we collect more than 10% of the population, then there's a chance that you're introducing observations that are not independent of each other. And so that becomes a problem. Now, this one is totally optional because, like I said, if you have a large sample, that's a good thing. So it's not something that I think, you know, should stop you from collecting a huge sample if you have the funds. But it is something to keep in mind that it would affect the independence of the observations. So here, right? And so this one's kind of optional for checking. N less than 10% means, or 10%, usually I just shorthand it to this, of the population is mostly if you're sampling from a small population. So it's mostly a concern if you're sampling from a small population. Is not usually a concern. But if we sample more than 10% of the population, we will likely have dependent observations, right? So we will likely have dependent observations, which goes against one of the conditions for assuming that we have a normal distribution, but it's optional. So it's not going to be a huge deal. It's not going to affect us, but it is something to keep in mind, right? If you're doing calculations on your own. Okay, so then the next condition that we have to check is the normality condition. And so the independence condition is that you have to have a random sample. Ideally, it's less than 10% of the population. And then the normality condition comes from, I have to have an expected number of successes has to be more than 10, and the expected number of failures has to be more than 10. And that's a count of 10, right? So it gets confusing with the 10% of the population and then a count of 10, but once you've done enough of them, then it starts to flow a little bit nicer. So if we know the population proportion, then we can find the expected number of successes and failures, right? Regardless of the sample size. Maybe I missed the chat there. If you could clarify. Oh, okay. Well, yeah, so we're going to talk about the sample size. I think maybe you're just thinking ahead to this next one. So what we need is an observed number of successes has to be, yeah, the sample size 1. Well, you can't do anything with a sample size of 1. And it wouldn't come from a normal distribution because we have to have n times p hat has to be more than 10, right? Or this is the same as saying more than 10 successes in the sample. I think it's probably greater than or equal to 10. Doesn't really matter. If you're on 10, you're fine, I guess. N times Q hat also has to be greater than or equal to 10. And that means we have to have more than, or at least 10 success or failures. Maybe I should say that. At least 10 successes in the sample and at least 10 failures in the sample. What does that mean? Means that if we have a 50-50 split, successes and failures, so if P hat is 0.5, then Q hat is 0.5, and then we would have 10 successes and 10 failures at minimum. So that means our minimum sample size, our smallest possible sample size is 20, right? But if you have collected a sample of size 20 and you only have 10 failures in there, then you need to collect a larger sample, right? And so this kind of tells us that the smallest possible sample size that we could consider is 20, right? And so sometimes you'll have N and P hat, and sometimes you'll just have how many successes out of a total sample size. And then from there, you can find the number of failures, right? So that was a long review, but it's all really important. So I'll end it there and we'll pick up right from there. Because today we want to talk about confidence intervals. And so we've talked about, okay, if I have a sample proportion, then that's my best guess at what the population proportion is, right? And so, but we also know that it's not going to be exactly the same, right? So there's going to be some error bounds, right? And that's when we introduce the standard error. And so now we want to formalize this concept of, okay, I've got this point estimate, this sample proportion that it was collected randomly. And so it's good. I can assume it came from a normal distribution. And so we don't want to just talk about the point estimate, our sample proportion. We want to say, okay, well, based off of that sample proportion, then I think a range of plausible values for the population proportion is this. Okay, so we want to give a range of plausible values. And so some notes here. So where am I from a page break? Kind of far away. So I'll just go for it here. 5.2 is called confidence intervals for a proportion. So the textbook has this really cute, intuitive example of, let's say you're at a lake and you're fishing, okay? And so you have two options for fishing. You could use a spear, right? And so you've seen some fish, you think there's fish in a certain area, and so you use a spear and you try to catch a fish, right? And so the spear is the sample proportion, right? Whereas the fish is the population proportion. So if you catch it, good for you, but it's unlikely that you're gonna get it right where it is, right? That's hard. So then the other option is, what if we cast a net instead, right? And so just think about it as throwing out a net and you're trying to catch a fish that way, right? And so a confidence interval is the equivalent of casting a net to try to catch a fish, as opposed to just the sample proportion, which is just the spear trying to catch the sample or the population proportion. Okay, and so P hat provides a single plausible estimate, right? Or a point estimate provides a single plausible estimate, and we'll call it a point estimate. What you'll see is this terminology of, big net for big fish. Exactly. Yeah. And so we're going to use the point estimate kind of generically. So then when we move into talking about other types of data, right? And so here we're talking about proportions, but then we're going to migrate towards talking about means, right? And so that point estimate, that terminology is going to stay the same. It just refers to different things. So that's nice. So p hat provides a single plausible estimate for p, right? The population proportion. But we know that p hat has a standard error associated with it. Has a standard error associated with it. So we use confidence intervals. So here we have a single plausible estimate. And so a confidence interval is going to give us a range of plausible values for P. So a confidence interval which I usually abbreviate CI, confidential informant, right? And so confidence interval, CI, just kind of, if you see CI, that's what I mean. And so a confidence interval provides a range of plausible values for P. Okay? So that's going to be the difference. Oh. Okay. One thing to keep in mind is we still don't know what P is. So that's kind of a problem. So we have this range of plausible values, but what we saw was that the sample proportions are all going to move around, right? They come from a normal distribution. And so we talked about, you know, there are some sample proportions that happen out in the tails. So then even if we cast a net around that sample proportion, we might not be capturing the population proportion. And so that becomes a problem, but that's also the idea behind the confidence interval, because we're only going to be 95% confident or 90% confident or 99% confident. And what that comes from is essentially the width of our net, right? And so the width of our confidence interval determines how confident we are that we've captured the population proportion. So the default confidence interval is going to be 95%. It gives us a nice trade-off of confidence, right? 95%, that's pretty reasonable, pretty high. And so we can feel good about putting that out there, but also we don't have to have a super wide interval in order to make that happen, right? We kind of are able to contain it within reason. So the default confidence level will be 95%. Because it provides a good trade-off between confidence, right? 95% is pretty high, and precision, right? A nice and tight interval, okay? And so the default confidence level will be 95% because, oops, it provides a good trade-off between confidence, right? 95% is quite high, and precision, the interval doesn't need to be really, really wide. The interval doesn't need to be very wide. Okay. So one example that I kind of like is how far away do you live from the school, right? So we understand. So if I ask you the question, how far away do you live from the school? And so we understand that there is some exact distance. We could figure out the exact distance that we live from the school, but we wouldn't do that, right? Because we don't need to, right? But we have a pretty good idea of what it is. And so we have this estimate. I have an estimate of, let's say, 10 kilometers, right? And so what we usually automatically do is we say 10 kilometers plus minus, let's say 3 kilometers. How did I decide on that 3 kilometers? Well, then you have the follow-up question of, okay, well, how confident are you? 90, 95, 99% confident, right? And so the problem with being 100% confident is that we would have to make our interval so wide, right? If I said, okay, I live 10 kilometers away from the school, right? So I live nice and close-ish, right? And so I live 10 kilometers away from the school, but then if I said plus minus 100 kilometers, that's pretty useless, right? Because I've lost that precision. I'm 100% confident that I have captured the actual distance to the school, but I've lost that precision, right? Because I had to make my interval so wide, right? And so this trade-off here between confidence and precision, that's where we get to the 95%. Because if I have to be 95%, I might say something like, oh, I live 10 kilometers away, plus minus, 2 kilometers. That's pretty good. How confident am I? I'm 95% confident. So that's that trade-off. In order to be 100% confident, you need to blow up your bounds of the interval to be so large. So it's like, so accuracy is hard, but yeah, definitely precision. And then, so you can think of it as accuracy and precision, but because we don't know what the true distance is, it's hard to talk about accuracy, but pretty much the confidence is essentially the accuracy and then the precision, right? And so we've got this trade-off, this kind of fine line that we're walking when we're trying to build these intervals. And so we've got a sample estimate, right? So a point estimate, that's going to be my initial guess, okay? So that's going to be your sample proportion. But then what we do is we put bounds around it, and I think of it as a buffer, right? And so so the problem becomes, if you think back to the normal distribution, those tails go to infinity in either end, right? So technically you would have to go to infinity, right? And it depends on the situation, right? But you'd have to go to negative infinity and positive infinity in order to truly have 100% confidence interval. But we never do that for that reason. It makes no sense. Right, so good. So we're going to have some estimate, right? So our best guess, and that's going to be our sample proportion. And later it's going to be our sample mean, right? And so we're going to have our best guess. And then what we do is we build bounds around it. So we build up this interval, and that's going to be our confidence interval. We still don't know, right? And that's why it's a confidence interval. We still don't know if we're capturing the population proportion. We still don't know what it is. We're 95% confident that we've captured it, right? But there's a graphic that I want to show you where that's not always true, but we don't know how close our sample is to the population. And so we just have to rely on, okay, I assume that I have a random sample. I assume it looks like the population. And here I'm 95% confident that I've captured the population proportion. So if we think about 95%, okay, and if we know that we're pulling from a normal distribution, okay, so I'll put this on a fresh page here. So since we know p hat comes from a normal distribution, we can figure out how much of a bound or how much of a buffer I need to build around p hat to capture the central 95%. Okay, so since we know p hat, the significance level, you guys are jumping way ahead. So the p-value is essentially, so the link, if you're aware of the significance level, so you're either 95% confident that the population parameter is in this region here. The remaining 5% is going to be, okay, so then I'm 5%. So if it's less than 5% that it's beyond that point, then there's that trade-off. Yeah, and I don't think it's very helpful. So I'm gonna leave it there because we're going to talk about hypothesis testing, obviously, and then we'll talk more about it. So let's focus on the confidence interval. So especially because most of statistics is moving towards just using confidence intervals instead of hypothesis testing. You'll see why in a bit. Sometime this week, you'll understand why. But it's also a little bit better, a little bit kind of, I don't know, you'll see. Not as cut and dry, gives us some wiggle room. So since we know p hat comes from a normal distribution, we can use it to build the confidence interval. Okay. So if I know that it comes from a normal distribution, so then here, let's say I'm looking at a Z distribution. A Z distribution is centered on 0. And so because I can always standardize a sample proportion because I have the standard error, and so I can look at the Z scores, and what do I want? What do we want? We want 95%, the central 95%. How can we do that? Well, we know we have a pretty good idea from the empirical rule, right? The 68, 95, 99.7 rule. So we think it's going to be around, it's going to be about -2 and about +2. We're not okay with those ±2 anymore. We need a little bit more precision, right? And so what can we do? We use the Z table and we can find these values, and there will be an easier way to do it, but it's good to understand what it's doing, because otherwise we're dangerous, aren't we? If I'm looking at the central 95% here, then I've got 5% split up, right? And so then I have an area of 0.025, 0.0250 here. All right, and so the area in the tail is 0.0250. What can I do if I have the area in the tail? I can backtrack to find a z-score. So let's go to the tables. Oh, that's from another time. Yeah, you can make that connection of alpha, but we're not talking about that because that would be too confusing for most people, I think, right now. Okay, so once we've talked about alpha, we can talk about that. So let's see here. I'm looking for the area that's closest to 0.025, right? And so 0.025, I'm kind of scanning here, 0.025, 0.0262, 0.0256. Hey, cha-ching. I landed right on it here. That never happens, right? Where I land on the actual value, but here we are. What luck. Looks like it corresponds to a negative 1.96. So then what that looks like here is we have Z equal to negative 1.96. So is that close to -2? Yes, it is, right? And that's where the empirical rule came from, okay? By symmetry, I know on the positive side, it has to be positive 1.96. Otherwise, it wouldn't be the central 95%. And so here I would have Z equal to 1.96. So from here, right, I can say, okay, well, 1.96 and 2 are basically the same thing. Okay, so we're all on board. It's just a little bit more precision, and that's what we're going to be using. So I'll make a note here. Notice that these are similar or very close. Be sure to use the more precise 1.96 plus minus 1.96. Okay, yeah. We'll talk about hypothesis testing. But we're not talking about hypothesis testing. Okay, so we will make the connection once we introduce it. Okay, it's actually always the probability that the null hypothesis is true. So just hold your horses. Okay, so notice that these are very close, but we're going to be using the more precise version. Okay, and so what we want to do is we want to take our sample proportion and we want to build a buffer. We want to build a 95% buffer. Okay, and so to build our confidence interval, our 95% confidence interval, around p hat, yeah, we need to build a buffer that's 1.96 standard errors away from the sample or the point estimate. We need to build a buffer that is plus minus 1.96 standard errors, because we talked about, okay, so these are actually standard deviations away, z-scores, or how many standard deviations am I away from the mean of 0 in this case. But now we're talking about p's, and the sample proportion comes from a normal distribution with a standard deviation, which we're calling the standard error, just so we don't get confused. Although saying it sounds a little bit confusing, but you can see why calling it the standard deviation doesn't really make sense, because it's the square root of p times 1 minus p over n. So to build our 95% confidence interval around p hat, we need to build a buffer that's 1.96 standard errors away from p hat. So what we get is we get p hat, keeps glitching out here in my pen, but it's okay. P hat plus minus, because the plus moves us up and the minus moves us down. So typically we do the minus first and then the plus, but just typical convention, we use plus minus. So that builds this buffer around p hat. Plus minus 1.96 times the standard error of p hat. Okay. Okay. So, all right, good. This 1.96, that's what dictates the confidence level, right? That's where the 95% comes in from, right? P hat, that's from the sample, right? So we get that from the sample. Even the standard error of p hat, that also came from the sample, right? Because here, this is the square root of p hat times 1 minus p hat over n. So all of these components, right, except for the 1.96, come from the sample. We can't influence those with our confidence interval or confidence level, right? And so here, this is the only value that dictates, clean that up here, that dictates the confidence level. Confidence level. Drew a blank there. Okay, of 95%, I'll say. Okay. In general, we call this the critical value. Okay? And we usually denote it by a Z star. Okay. So in general, we call this a critical value denoted by Z star. Okay. At least in the case of proportions. Okay, but for now, we'll start with just calling it Z star. So in general, we can build any confidence level, or we can build any confidence interval by p hat plus minus Z star times the standard error of p hat. Okay. So notice how I'm holding off on actually plugging in the value here, because I want to show that this is generic, right? We've got a point estimate plus minus some critical value times the standard error of that point estimate. Okay. Maybe I'll bump this up and highlight that here. So we've got maybe this, we've got a point estimate. We've got a critical value. And then we have the standard error of the point estimate. Okay. So we can build any confidence interval if we know what the point estimate is, if we know what the standard error of the point estimate is, and how to find the critical value. That sounds like a lot, but we're really just laying the groundwork for being able to build any confidence interval for any parameter. Okay, so that's not necessarily just the population proportion that we're trying to capture. We're going to try to capture, does the standard error formula? Yes, it does. It comes from it depends on the distribution that you're pulling from. Yeah. So that's one of the things that, as long as I give you what distribution you're pulling from, right, then we can use that to figure out confidence intervals and later hypothesis testing. And so, okay, so if we have this framework, let's focus, let's go back to the p-hat example, right? We've got a sample proportion and we're trying to build a confidence interval. And so what we said was, okay, I need a critical value. And so what if I asked you, you could have a note somewhere that says, okay, for a 95% confidence interval, I need to use a Z star of 1.96. What if I asked you for a 99% confidence interval? Right? Okay, here we go again, right? So what if we want to build a 99% confidence interval? Same idea, here we go again, right? Knowing that we're pulling from a normal distribution, we can bring that back to a Z, which is centered on 0. And now I want to force this central 99% between two values, right? And so, and I'm hurrying through this because we're going to have a shortcut, not just software, but also in the table. So even if we didn't have software, we'd still have a shortcut. 99% means 1% is left over, but it's split evenly between the two tails. And so that means I have 0.5%, which means this must be 0.005. Let me just confirm. 0.5 divided by 100 is, oh great, it gave me scientific notation, 1, 2, 3, cha-ching. Okay, nice, thank you. So what I'm looking for is an area in the tail that's closest to 0.005. Okay, so I go back to my Z table and I'm trying to find 0.0047. And let's see here, 0048, 49, and 51. Uh-oh, what am I supposed to do here? All right, let's highlight those. They're both 1 away from where I want to be, right? And so let's see here. I could do something crazy, like land in the middle here. So let's just see which values we're dealing with here. Negative 2.57 or negative 2.58, right? How about I go, I can't remember, negative 2.5. I would go 7.5. but but I'm trying to remember what the shortcut table says. Okay, I've held out long enough. I guess I'll jot these down and say negative 2.57 or negative 2.58. Let me see what the shortcut table does. So instead of having to figure this out every time, then what, of course, someone has done is just make you a little shortcut table that you can use to find those critical values. It's actually in, and this is kind of where it gets weird. It's in the T table, which is the third set of or the third table in that handout. So here we haven't used the T table yet, but we will. It's just catching up, sorry. So here, all I want you to focus on for right now is, well, we've got these confidence levels. And down at the bottom here, I have a row of Z stars. And we'll talk about the T table later. So here we have more precise values. So what I'm going to do is I'm going to chop up this guy here, copy, bring it into our notes, paste. Okay. And then I'm just going to ignore the midsection here for a bit. Copy. Oh, paste. Make sure they line up here. So here, you can see, of course, they all kind of keep going, right? And so if I want a 99% confidence level, then my Z star that I'm going to use is 2.576. So you can see that that is somewhere between negative 2.57 and negative 2.58, but we just get a little bit more precision, right? With the slope of the curve, right? We know it's not going to be smack in the middle, but it's pretty close, 2.576. Okay, and so to easily find, oops, critical values for most confidence intervals, you have the tools for finding it for a confidence interval that isn't on this page, right? If I wanted a 97% confidence interval, you know how to do that, right? And so, oh, I feel like it's all paused here. Sorry, just see if it's catching up. Okay, I think we're back in business. I'll just repeat in case, yeah, I think it glitched out. I'm seeing a thumbs up, so that's good. So to easily find critical values for most, not all, like 97% is not on here. You have the tools for finding that, right? But for most confidence levels, we can use the T table. And so here the T table is table C. That's what it's called in this set of tables. Everyone has their own naming conventions, but for now we're just ignoring everything in the middle here because that's from the T distribution, but the T distribution approaches a Z distribution, so that's why we have Z. I don't know, 97%, I don't know, I haven't done it. So here, right, we've got 99%. We're going to use a Z star of 2.576. So for a 99% confidence interval, we will use Z star equal to 2.576. Yeah. Okay. So now we have that shortcut. So that's not going to be an issue, right? But that's where it came from. We know we're pulling from a normal distribution, and so we could calculate the Z score, right? And so here, so now we have kind of all the tools for building any confidence interval. Okay. So the thing about confidence intervals, why we're only 99% or 95% confident, is because if we pulled many, many, many samples, right, we already saw that each sample is going to have its own sample proportion. Those sample proportions are going to be more or less around the population proportion. But we also saw that some of those some of those sample proportions are far off, right, far out into the tails. So that's going to be reflected in our confidence interval. So we don't know what our sample proportion looks like in relation to the population proportion. So that's why we're only 95% confident. Okay, so let's see here. I feel like I had it. Oh, must have scrolled around here. I'll just go there. Sorry, guys. Ah, there. Copy. Come on. I'll always give you the confidence level, but I won't give you the critical value, if that's what you mean. But I tend to use ones that are in the table. So I'll always give you the confidence level. I'll say things like make a 99% confidence interval for the population proportion, and then you'll know what to do. But so what we saw and what we're looking at here is that if we pull even 25 different samples from a population where we know the population proportion is 0.88, right? So here we happen to know what the population proportion is. We wouldn't know that in practice, right? But in this case, we're kind of backtracking and saying, okay, what do these things look like if we knew what the population proportion was? So here's the population proportion at 0.88, and you can see most of these, even the sample proportions are pretty close to 0.88, right? So the sample proportion is the dot here, right? And then we've built these bounds, these plus minus bounds. So these are our confidence intervals. So even though this p hat is quite a ways off of 0.88, once we build our bounds, right, our confidence intervals, then the confidence interval cap proportion, they're the same. Sorry, it keeps glitching out. I don't know what's going on, but here we are. So notice that even though some of these sample proportions are quite a ways off right here, once we build our interval around it, it still captures the population proportion, right? There's only one that doesn't, 1 out of 25, right? 1 out of 25, you can try it. 1 out of 25 is 0.04, right? And so, or rather, 24 out of 25 actually did capture it. So 96% of these captured the 0.88. Okay. And so here, This is probably a 95% confidence interval, I think. Yeah, I'm assuming. So here, 95% confidence interval, 96% are capturing the population proportion. So that's really good, right? We don't know the population proportion typically, right? And so here we see that 24 out of 25, which is 96% of the intervals, capture P equal to 0.88. So it's really important when we're interpreting our confidence intervals, and I know we haven't built one yet, but when we have our interval, we have to interpret it. And so when we interpret the interval, it's this idea of capturing the population parameter, right? The parameter is just a general term for a measurement from the population, right? And so in general, what we're trying to do is capture the parameter, right? And so this idea of, okay, I'm 95% confident that this interval captures the parameter, because we don't know what the parameter is, right? We're trying to catch that fish, for example, with our net. We don't know where the fish is, and so we're just kind of going for it. Okay, and so when we interpret our intervals, that idea of we're only so certain that we've captured the parameter is going to be really important. So once we have built our interval, or our confidence interval, I should say, proper, our confidence interval, we need to interpret it. Why is it? It's like my Apple Pencil's running out of ink somehow. I'm not sure what's going on. Why is it acting like this? I don't know. We need to interpret the interval. The most important thing is that we are some percentage confident that the interval captures the parameter. Okay. And so it is important to remember that we are, and I'm going to say blank percent, right? Just leaving room for any confidence interval. So we're blank percent confident that the interval captures, okay, and so that's that idea of capturing the parameter in general is the most important part. So that we're 95% confident that the interval captures the parameter. Just as a reminder, the parameter is what? It's a measurement from the population. Measurement from the population. Okay, so in our case, right? So from our example from last day, from the example last day, we found that P hat was 0.887. And we also said that the standard error of P hat is the square root of 0.887 times 1 minus 0.887, over, I think it was 1,000. So here, I just want to jump into it with some values. And so we're going to use that the standard error of p hat is 0.010. Yeah. I have rounded it, but that's okay. Yeah. So if I want to make a 95% confidence interval here, right? So here I might say something like construct a 95% confidence interval, only because I'm short of time. Oh yeah, but a proportion is a binomial, right? So because a binomial is success failure, right? And a p hat is the proportion of successes, right? So they're the same. So construct a 95% confidence interval. It's just what type of problem we're dealing with kind of changes things, but the ideas are the same exactly. So construct a 95% confidence interval. So first thing I want to do is I want to build up my framework, and you don't have to do this, but I just want to show you one time. We've got our point estimate plus minus our critical value times the standard error of the point estimate. There. Okay. So in our case, we had p hat is our point estimate, plus minus a z star is going to be our critical value, and times the standard error of p hat in this case. So now I remember that z star for a 95% confidence interval is 1.96, which we can confirm with our table, right? Want a 95% confidence interval. I have a Z of 1.960, so I'll just use 1.96. We could have used any of these confidence levels, but I usually stick, so typically we just stick to 90, 95, 99, that's it. Right, might go rogue and go for something weird, but usually that's not the idea of the exercise. The idea of the exercise is the interpretation. So we have a Z star of 1.96. We also know our p hat. Our p hat from up here is 0.887 plus minus 1.96 times 0.010. Yeah. So this here, this 1.96 times 0.01, I'm going to do here on the side here, 1.96 times 0.01. So I get a buffer essentially of 0.0196. So 0.887 plus minus 0.0196. So now I have to go down 0.0196 and up 0.0196. So I get 0.887 minus 0.0196. How you report these intervals is using round brackets. So round brackets for the intervals, and you have your lower separated by a comma and then your upper bound. Okay, so here I'm going to show you what it should look like, and then I'll kind of talk about the components. So between 0.8674 up to 0.887 plus 0.0196, 0.9066. Yeah. Use round brackets for the interval. And what we do is we use round bracket, lower comma upper. Okay. So one thing to keep in mind is if you end up listing the upper comma lower, that doesn't exist, right? The interval from 4 to 2 doesn't exist. The interval from 2 to 4 exists, right? And so you have to be really careful about your calculations. So one thing that throws people off a lot is because it says plus minus, typically our minds just go to doing the upper bound first, right? So 0.887 plus this, and then 0.8887 minus this. But you have to make sure that you put the lower and the upper bounds in their proper places, right? And so order here, order is really important here. Since, for example, 2 to 4 exists, right? And on a number line, it looks like this. So between 2 to 4. Open dots, but we'll focus on that. But 4 to 2 doesn't exist. So you want to be really careful that you put it the lower to the upper. Okay. So what I would love for you to do is take this interval and try to interpret it. You might have to refer back to the actual example from last day. It's in the textbook too, but so try your interpretation, and then that's where we'll start on Thursday. If you have any questions, let me know. Otherwise, see you Thursday. Still says it's recording here. Okay, stop recording.